Okay, I think it's time to start. Let me first start by presenting myself. My name is Samhaa El-Beltagy. I am currently the Dean of the School of Information Technology at New Giza University in Egypt. But I prefer introducing myself as a researcher in the field of computational linguistics, and especially Arabic computational linguistics. Today I'll be presenting a paper by the title of QDetect, an intelligent tool for detecting Quranic verses in any text. And this paper was co-authored by Professor Dr. Ahmed Rafea at the American University in Cairo. Okay, let me see. Okay, so what is the motivation for this work? The motivation for this work is that during the past decade or so, we have seen an explosion in the generation of Arabic textual data. And I think it's not a secret that this was largely the result of the uptake of social media platforms. And observing existing data shows that verses from the Holy Quran are often quoted in this data, especially the one, if we're talking about social media, then a lot of people quote the Holy Quran just as we do in our everyday life. And we do that because in Arabic-speaking individuals, they usually like to express all sorts of emotions ranging from sympathy to joy and anger using religious expressions, not necessarily the Holy Quran, but often using the Holy Qurans. When someone is frustrated with someone or something, they might end up saying Hasbunallah wa ni'mal wakil. If they have been subjected to some injustice, you find them saying وَلَا تَحْسَبَنَّ اللَّهَ غَافِلًا عَمَّا يَعْمَلَ الظَّالِمُونَ, and so on and so forth. The fact is, as Arabic-speaking individuals, we use Holy Quran a lot. And this is not, we just don't only use it on social media, but it's also, of course, quoted in religious sermons and in public speeches. So many applications can benefit from the automatic detection and annotation of those verses. Examples include sentiment analysis systems, emotion detection systems, automatic speech-to-text transcribers, among others. And the reason, let me give you just a few examples. In sentiment analysis, for example, if someone is quoting Quran, it could be, if we can normalize it or just use the name of the ayah instead of the whole thing, then it is less likely to confuse the sentiment analysis system than individual words. In automatic speech-to-text transcription systems, it is a well-known fact that when the Holy Quran appears in any text, it is usually, especially if we're talking within a formal context, usually we like to actually annotate and specify which surah and which exact verse number this surah has or this verse has originated from. So these are just a few examples of where we can use automatic detection of the Holy Quran. Okay, so if we talk about the problem statement itself, we can say that the Holy Quran is divided into 114 chapters or surahs, and each chapter contains a varying number of verses, and each verse contains a variable number of words. The total number of verses in the Quran is 6,236. And when quoting Quran, people do not necessarily quote an entire verse, but they often quote parts of a verse that can be found in the middle of a long verse. Okay, so in order to detect Quran in any text, not only does the system need to detect a whole verse or whole verses, but also verse fragments. A single piece of text can contain multiple verse fragments or verses that are either consecutive or isolated. And when building a system that we were trying to build, we have to be able to match all of those. So the goal of this work is basically to try to identify any verse fragment that is equivalent to or greater than 3 words in any piece of text, and match it to its originating chapter and verse number, and to do so as efficiently as possible. Okay, and there are some factors to consider when approaching this problem, and these include the fact that we were talking about social media, and in social media people usually try to quote a verse of Quran from memory, and what happens is that when people try to quote Quran from memory, they may forget a word, they may replace it with another word, or they may misspell it. Okay, and it's very common that, for example, to write takun, it's pronounced takun, like in Quran it's just a ta and kaf, but if we are going to write it as we hear it, then we could actually misspell it like this, and the same for al-muta'ali. Another thing that had to be taken into consideration is that a single verse from Quran can actually occur in multiple chapters. For example, the text Allahu la ilaha illa huwa al-hayy al-qayyum, it's known that this is from Ayat or Surah An-Nur in Al-Baqarah, but it's also a whole verse in Surah Al-Umran, and it only appears as a partial verse in Surah Al-Baqarah. So an intelligent system should be able to disambiguate between those, and we can only disambiguate if such a verse is followed by other verses or verse fragments from the same chapter or surah. Some verses in the Holy Quran are 1 or 2 words long only, like Alif Lam Mim. There are many examples, and they should be detected. But in order to do that without actually creating a very noisy algorithm, we have placed a condition that says that we can only detect them if they're immediately preceded or followed by other verses from, of course, the same surah. I mean, they should be in their context. Okay. Here is this graph shows the distribution of words in Quranic verses, and the reason that I'm presenting this figure is to show that this is a pattern matching problem, basically. And in order to understand what kind of patterns we need to generate and match with, we produced this histogram. So, for example, the majority or a large number of verses in Quran are made, this is 500 plus verses, have just 4 words. Others have 5 words, and so on and so forth. But when generating the number of patterns that we need to match with in order to satisfy the problem definition or the goal of this work, we discovered that the number of patterns is equivalent to 626,830 patterns, which is a huge pattern space. If someone attempts to match this pattern space using regular techniques like regular expressions, this is not going to be efficient. It doesn't work with such a huge pattern space. So let me formulate the problem in a more formal manner. We state that given some input text T of length and words and a huge pattern space P, which is equivalent to this number, where K is approximately equal to this number, we want to find all patterns P of I that occur in T, and we want to do that in all of n time. Okay, O of n time means that we want to scan each word only once, and we don't want to do more than that. So I'm now going to present the actual model that we've developed to do that. And the proposed model consists of two stages. In the first stage, all verses are stored in a compact data structure to facilitate the matching process. This is called the preparation step, and it is done only once. Okay, so we do that once offline, and then we are ready to match any text. And in the second step, this is where the actual detection or matching takes place in any piece of text, and this is called the matching step. So in the preparation step, each verse in the Holy Quran is read and normalized. Normalization of the verses is done by removing all diacritics, unifying all forms of alif and ya and ha, and this is done word by word. And terms in each verse are scanned one by one and inserted in a data structure that is composed. And this is actually where things might get a little confusing. I hope I'm going to show a figure that I hope will clarify things. But we've designed a data structure composed of a linked hash tables. Okay, so you have a top level hash table that actually links to nodes, and each of those nodes is in itself a hash node. So each entry in the top level hash table is a key to a node that has a hash table that stores its children, which are also nodes. I know that this might sound confusing, so I hope that the figure I have on the next slide will clarify things. And generation of patterns is done on the fly as verses are being read. So let me show you the figure that I hope will clarify this a little bit. Okay, let's say that we start by scanning the Holy Quran. We start by Bismillah ar-Rahman ar-Rahim. So we start by the word Bism, and this is the top level hash table. We check if Bism is included in this table or not. If it is not included, we create a node for it. But if it is included, then we just add information about the current verse that we are reading. So each node contains information about the verse in which it appears. This node is not expanded, but the following one is. So Bismillah, and here we can see that this is again the top level hash table. So if we expand Allah and we try to follow the following words, it has a node, and the node is another hash table that contains other nodes. So in this node, we can see all the words that appear after Allah in the Holy Quran. So of course, this is not a complete representation. This is just a snapshot because this is a huge data structure. So here Allah can be followed by وَالَّذِينَ الرَّحْمَنِ بِنُورِهِمْ لَذَهَبَ يَأْمُرَهُم. And again, I'm not expanding all of this. I'll just expand Allah وَالَّذِينَ. So if we follow this, Allah وَالَّذِينَ مَعَهُ, وَالَّذِينَ آمَنُوا وَالَّذِينَ كَفَرُوا, and so on and so forth. So the matching process is highly dependent on this table being built. I think I'm running out of time, and I'm the chair. I should not be doing that. So I'll try to speed up things a little bit, but it was really important that this part is covered properly. I'm going to skip this, and I'm just going to go to the matching step. So in this step, we aim to find all verses or verse fragments that occur in some text T. And we do that by scanning the words in order. And of course, we have to normalize each of those words again. And so after we normalize them, we start checking, is this word that we've just seen in the top level hash table? If it is, then there's a potential that this could denote the beginning of a verse. So we start following it. Okay, we check the next word, and we check if the next word is in its children, and so on and so forth. So the next term is then the next term in the text is then looked up in the table, and this process continues until we either encounter a three word sequence, which means that we have a match, or we terminate before that happens. Let me show you a couple of examples. This is an example. This is actually a tweet. Okay, and when this tweet is annotated by the developed system, okay, you can see that here this part تحسبهم I apologize for my pronunciation of Arabic. I'm sure that I'm offending some I mean, if you have a strong linguistic background, I might be offending you, so I apologize for that. تحسبهم جميعا وقلوبهم شتى. So this is a verse from Surah Al-Hashr, and here in the annotation you can see that it's preceded with three dots, which means that there are words or terms from this verse that are missing before this part, and it's also followed by three dots, which means the same thing. And we have another annotation from the same verse, which is Al-Hashr 14 بأسهم بينهم شديد. Okay. So if we're going to do some analysis of the performance of the algorithms that has been developed, we can say that the best case performance is 0 of n, but we can also go to there is the worst case performance, and this happens when all the words in the input string can be found in the top level hash table, and when each of those words is followed by a word that is also in the next table, but the third word is not in the active table. This is a very highly unlikely case, but if it happens, it can have a cost of up to order of 3n. On average, we expect that the actual cost of applying the presented algorithm is in the range of O of n plus c, where c is a constant and it's small enough so that the algorithm can be still in the order of O of n. We've carried out some techniques for error detection, but I don't have time to go through the error detection techniques. But applying any error detection mechanism, unfortunately, is much more expensive than if we're attempting to do exact matching. So in order to evaluate this work, we had a data set consisting of 473 tweets. And we had someone, a human being, annotate those tweets in order to indicate whether they contain a verse or verse fragment from Quran or not. QDetect was then applied to the tweets to see whether it matches with the human annotation or not. I'll just present the result. The tool was able to detect 93 verses. Let me just go back a little, and I'm going to say that out of the 473 tweets, there were 95 verses in those tweets. So of the 95, the tool was able to detect 93 verses, of which 90 were correct. Okay, so the precision was 96.8%. The tool missed the detection of 5 verses. Those were false negatives. So the recall was 94.8%, and the F-score was 95.8%. And this is one of the things that that was actually considered as incorrect. The system was detected وصية يوصي بها as a verse, and I think that one of the reasons this error occurred is because the stop list, we have a mechanism, and biha wasn't included appropriately in the stop word list. This is one of the things that were missed, وليال عشر, and the reason it was missed because it doesn't meet the minimum length requirements. So in conclusion, this paper presented a model for full or partial identification and detection of Quranic verses in any piece of text in a time that is proportional to the length of the text. And error detection is much more expensive in terms of time, but can be useful for many applications. The model is available as open source code and can be used in applications that require the identification or annotation of Quranic verses. And the result of evaluating this model show that it is consistently capable of identifying Quranic verses correctly. I do have a related work section in the paper, but I did not include it here. There's not a lot of work that has been done in this area, but it is in the paper. And in the future, we aim to experiment with a larger data set, as well as target speeding up the error detection features. This brings me to the end of my presentation. I'm sorry if I've taken all my time, actually. The good news is, or I don't know if it's good or bad, but the next presentation, the presenter for the next presentation cannot make it. So there is time for questions if anyone wants to ask me anything. Sorry. Okay, there seems to be no questions. Okay, Dr. Ashraf, please go ahead.
Thank you, Professor Samhaa. Nice work, and it's a bit different than what we have seen in the morning sessions. What would you report when you have a sort of 3 words that match more than one verse? Will you be retrieving all of them, or
all of them?
All of them. So they will be quoted like one after the other where they have been. Okay. Yes. And do you have an idea about the size of the hash table for?
Yes, the size of the hash table is actually included in the paper. I can't remember how big it was right now, but because it is we have 6,800 plus data patterns, but it's using a compact representation, because anything that's repeated, there's no redundancy. So it doesn't take up a lot of space, but I don't have the exact number right now. And to be honest, I don't know if I've included it in the paper or not. I think I did do the exercise of actually running code to extract its size. But if this is something that you're interested in, I could send you that information via email or privately.
Yeah, because it can help. I mean, if you look at the actual linked list for each level, that could give you also another idea of using multi-hashing functions at different levels. Maybe that would optimize the time. My last question, if I can, it's about what if I make a spelling mistake? And I guess you are, that's why you are searching, in your talk, you said it's order n. But if you are using the hash code for every word, then maybe that will give you a sort of a constant time, order 1, yani in general.
I think you cannot have a order 1, Dr. Ashraf, for this problem. For the same, I mean, you need to scan the n. Here is n. N is the size of the text that you're trying to find matches in. So let's say that you have a piece of text that is 100 words long. Okay, right. You cannot, the lowest, I don't think that you can get anything that is less than order of, it's, okay, the text has 1 or more verses within it. So you have to scan the words one by one. So right. How are you going to get it in anything that is less than order?
For each word, for example, for the first one, you compute the hash code and then you go directly to the first level?
Yes, exactly.
Yeah, that's my question actually, because if I make a mistake there, then the computed hash code would be wrong, right?
Exactly. Yes, it
Yeah.
will be wrong, and we have, in order to accommodate for that, it's not the if in the middle of let's say it's a long verse, and in the middle you made a mistake. I just didn't have enough time, but I had a slide in there about the fact that we use Levenstein distance, but again, in order to actually try to match this with all the children. Uh, I want okay, let me give you an example. Let's say قل هو الله أحد, even though this was really easy, but قل has been detected, and Allah, let's say that the person for some strange reason has misspelled Allah.
Right.
That's not very common, but I'm just I'm just stating that as an example. So قل will be detected, and then when Allah, you take a look at the next word, which is not actually Allah, and you look at the children for this node, and you discover that this is another hash table. So you're looking up in this other hash table, which is a child of Qul, and you discover that this misspelled word does not exist. So you start this, and this is why I'm saying it's expensive. And if you have any ideas, that would be great. But you actually, if you're doing error correction, then you get all the children of Qul, and you calculate the Levenstein distance between Allah and those. And if it's smaller than a given threshold, then you may assume that it should have been the other word, and you continue the search process. But this is, I mean, it's not because each node Qul, and you just compare with whatever is next to following it. But it is expensive. It is expensive if you're doing spelling correction.
Thank you. Well done again. Thank you.
Thank you very much, Dr. Ashraf. Okay, do we have any other questions? Okay, as I just stated, unfortunately, the speaker for the next presentation is not going to be able to join us. He had some unfortunately, his wife passed away. So these are exceptional circumstances. So we are going to break now. If you'd like to join the other session that is in Hall 2, please do. Otherwise, we'll reconvene at exactly, I think, let me check I think it's 3. I'll check the schedule really quickly. So, okay, the next, we have a break until 1:40 GMT. Okay, thank you all very much. Okay, there was a question by Men. Okay, thank you, Menwa. It identifies, okay, Menwa is asking, how does your algorithm identify the beginning of the verse within the text? It looks up every word, Menwa, and if the word is in the top level, because this is where any valid start of a verse is in the top level hash table. So if it's there, it starts looking at the next word to see if the sequence is correct or not, and if it finds a complete sequence, then this is how it identifies the whole verse. I hope I've answered your question. Thank you.